So here we are in section 2.2, the derivative of a function. This is a big deal, everyone. This is a big deal. This is like the thing here of Calc 1. So we have a function, and so the derivative of that function is defined by this. So I want you to notice in the past couple sections, we've seen these like things with the limit, and we've seen a and we've seen t, and we saw like a little bit of h, but like not a lot of h yet. Now we're going to see a lot of h. So this is when you take the derivative of a function, this is us taking the derivative of a function using the definition. This is the actual definition, the limit definition of the derivative. And when we finish with finding this, our function will still be a function. And that's a really important thing to know. We will not be ending up with just a number right away. We will actually be having a function, finding the derivative, and we get a function. So that makes sense because this is a function. It is f prime of x, which is still a function. Now, there is some alternative notation. So depending on what you're reading and what you're looking at, you might see y prime. So we have f prime of x, you might see y prime. You might see df dx. So that's the idea of taking a derivative. So notice the d there, derivative of f with respect to x. So df dx is usually how that would be said. You might see dy dx. You might see d dx of f of x. And you might see d of f of x. But I will tell you that in general, mainly what you're going to see, you see obviously a lot of f prime of x. You see y prime quite a bit. You see this, and then maybe some of this. The other two, we just don't see them as much. So it's kind of in order of how frequently you will see the different notation. But they do all mean the same thing. It is alternative notation. So let's start out by finding the derivative of this function right here. This is a quadratic, we know that. And when it says use the definition of a derivative, it means this idea of the limit. And so all we need to do is basically plug in what we can plug in, and then just simplify, evaluate, and at some point we should be able to take our limit. So graphically, what this is saying is if we add h, and h is just some little bit of difference between x and x plus h, what happens is h gets very small. And I'll show you a video of that. So I just want to show you graphically this idea of the limit as h goes to 0. So I could not find an applet where they were using x. So this applet uses c instead of x, but it is the same thing. So when you see c, just picture x. So what's happening is, in the limit definition of a derivative, we have f of x plus h minus f of x over h. But really, it's over x plus h minus h, because we have one point that is x f of x, and we have one point that is x plus h f of x plus h. But when you take x plus h minus x, which is what the difference is between the x values in the denominator, you end up with just h, and that's why there's just h there. So what that is the slope of this secant line. So that is the slope of this line. We know that that is what the m is. It is a slope, in this case, slope of a secant line. But when we take the limit, that's the big deal. When we take the limit, we're looking at what happens as h goes to 0. And what that means is we're looking at what happens as c plus h in this graph, or x plus h in our definition. As h goes to 0, it's talking about the one point getting closer to the other point. So as h goes to 0, c plus h is getting close to c. And so if I just move this, what's happening is I'm getting closer and closer to c, and what you should see is that that secant line that we started with ends up being a tangent line. And of course, that is the big idea behind the derivative. It is the slope of the line tangent to a function at any value. using the limit definition of the derivative, finding f prime of x. And so that's what it looks like graphically. And so once we find our examples, that'll give you a better idea of what the ending looks like once you use that limit definition. So first, what we need to do is think about f of x plus h. We have f of x. It is x squared minus 3x plus 2. F of x plus h just means take x plus h and plug it in. And plug it in everywhere where you see x. And then if you want, the first thing you can do is you can simplify it and then, get into this big idea of the f prime of x, blah, blah, blah. But we have f of x plus h. We have this. I'm going to simplify it. I'm going to multiply out x plus h squared. So notice that's x squared plus 2xh plus h squared. And then we have our minus here. So minus 3x, minus 3x, minus 3h plus 2. And then what I can do now that I have that, that's the only thing I didn't have, now I can plug that into my f prime of x. So I have limit as h goes to 0. You're always going to see this. And then I can put what I just found, which is x squared plus 2xh plus h squared minus 3x minus 3h plus 2. But I'm not done because that's just this top piece right here. Now I need to subtract f of x. So now I'm going to subtract that quadratic. Understand that subtracting that quadratic just means changing the sign of everything that, every sign that we have in the quadratic. So I'm going to subtract x squared. I'm going to subtract a minus 3x. And I'm going to subtract 2, a positive 2. And I'm going to put that over h. So this is what happens when you use the limit definition of a derivative. But the exciting part comes now. So what we do now is we take a look at what we have and we see if anything simplifies. Notice that right now if we took the limit, notice the denominator is h. So, well, that's a problem. Because with the denominator being h and we're looking as h goes to 0, we can't just plug in 0 for our limit because we have 0 in the denominator. And we'd actually find that we'd have 0 in the numerator too. So what we do is we use this, and now we just simplify anything in our numerator that can be simplified. And that's what I mean by fun, because you might be like, well, that's not fun. But you can take x squared, and you can subtract an x squared, and you can take a minus 3x, and you could add a minus 3x, a positive 3x, that's 0, and you've got a positive 2, and you've got a negative 2. And so all these things have simplified with each other. And now we just have to think about what's left. And now here's a big hint. The big hint is, if you have done this right, everything that is in my numerator right now should include an h. So I have 2xh plus h squared minus 3h. And the reason why that's so important and needed is because, of course, now that I have h in every term and I have division by h, well, now I can factor. And then I can take my limit and not have 0 over 0, which we know is a problem. So I'm going to take out that h. I'm going to have 2x plus h minus 3. I'm going to divide that by h. And like I just said, now that we've factored out that h, we have an h in the denominator, so that's a factor. That's the only factor in the denominator. So now we're just left with this limit. You know what? I'm actually going to move it a little more over here. I don't want it to cover my face. I'll actually bring it back over here just so I have enough space. Limit as h goes to 0 of 2x plus h minus 3. Now, when we plug in h being 0, we're okay. We get 2x plus 0 minus 3, or 2x minus 3. So this is our answer. The derivative of what we have above, just because we have so much writing here, the derivative of this function is this function right here. This is not necessary, but just because there was so much writing, this is f prime of x, the derivative of that quadratic. Let's take a look at a couple more examples here. Honestly, it's just a lot of algebra. These types of examples here with the definition of a derivative are just a bunch of algebra. You do the setup and then you do algebra. So if you are strong in algebra, you are going to be in really good shape. So notice this is g of x, and you might be like, well, that's not by definition. You just make g prime of x. So of course, any function, we just put the prime there, g prime of x. The reason I'm not going to do any side work here is because the limit as h goes to 0, excuse me, different notation here, but the limit as h goes to 0, just think about what g of x plus h is. Why I fight with my eraser here. There we go. Okay, so just think about what that is. We've got the limit as h goes to 0. In the numerator should be g of x plus h. That is simply 3 over x plus h. And then we subtract the function, which is 3 over x. And then we just divide by h. So this is the setup here. And I don't know if you know, but this is simply a complex fraction. Notice we've got fractions in the numerator. Notice the whole thing is a big fraction. And so this hopefully should take you back to your algebra days. There's a couple different options for how to simplify this because, of course, hopefully you notice if we plug in 0, we get 0 over 0. So if we want to find the derivative of this, we've got to do something. So there's a couple different options. You can create common fractions that have common denominators so that you can combine the two fractions in the numerator. You can also multiply top and bottom by the common denominator. That will also rid you of your fractions in the numerator. If you have issues with this problem, just Google simplifying complex fractions, because that's all you're doing here is just simplifying complex fractions. That's the algebra part of it. So what I'm going to do, hopefully, let's see, try to do this the best I can here. I'll make these like fractions. So I'm going to give them the same denominator. So one of them has a denominator of x and one of them has a denominator of x plus 4. You might be like, what's that about? So the big thing to see with that is those, although they share like terms, you have an x and you have an x, they do not share any common factors. X and x plus h do not share common factors because it's x plus h, not x times h. Because of that, the lowest common denominator is the two things multiplied together. So this fraction needs an x, this fraction needs an x plus h. So then, of course, the top needs it as well. There we go. And then, we just go from there and simplify and see what happens. So now we have the limit, don't forget your limit, as h goes to 0 of 3x. And so I'm going to combine my two fractions here. So I'm going to have 3x minus 3h. So I'm doing this subtraction here, and then I'm going to put them all over that x times x plus h. And then, of course, that's all over the h. So don't forget all those pieces there that we have. But now, what we notice is that now it's time to start simplifying and see what happens. So now we have this 3x, which simplifies with this 3x. So that's going to be super helpful. So all we have in the numerator is a minus 3h. I'll do a couple more steps here. We're almost ready to take our limit. So the limit as h goes to 0, now we have a negative 3h divided by an x times x plus h. That division by h at the bottom there, the division by h, you want to remember that dividing by something is the same as multiplying by 1 over that something, or the reciprocal of that something, depending on what that something is. So what I mean by that is, if I have 7 and I divide it by 2, that's the same as 7 times 1/2. And so in this case, division by h is the same as multiplying by 1 over h. And you might think, well, why did we do that? So understand that what this does is it takes the complex fraction. It's no longer complex. It's just this multiplication that we have. But bigger than that, we have h, and in h, that's simplify. That's key, because now I want you to see that when we look at the limit as h goes to 0, we have negative 3 in the numerator, because it's just negative 3 times 1, and the denominator is just x times x plus h. We no longer have a factor of h in the denominator, and so now when we look at this limit as h goes to 0, we just end up with a negative 3 over, any guesses? So the idea here is this is going to 0. Now we can plug in and get something that is legit, that does not have issues like the 0 over 0, and we get a negative 3 over x squared. And that is our answer. So just a reminder that it's g prime of x is negative 3 over x squared. Just as a side note from what we talked about in section 2.1, what this is saying is that negative 3 over x squared is the formula for, it's a function. It is a function, but it's telling us the slope of the line tangent to the function g of x equals 3 over x at any point. So if we know an x value, we could put it into there, and that's going to be the slope of the line that's tangent to that original function at that point. So don't want to forget that. That's the big idea. All right, let's do one more, and then I'll take a break from this video. So now we have another f, so I'm going to say f prime of x, and we've got a square root. Nobody was probably too surprised to see a square root, but of course that square root trick is going to come back to us. So we are going to do, oh, I guess I was thinking about doing, first starting with doing f of x plus h, but I think we'll be okay. So I need my limit as h goes to 0, because I'm just going to take the derivative. Okay, so now we've got the square root of, we need f of x plus h. All it is, change x to x plus h. That's it, that's it. And then we subtract our function, and then we divide by h. You might not be surprised to find out that if we just plug in 0 right now, we get 0 over 0, and that is a very big problem. And so what we need to do is use some sort of algebra trick so that we can kind of get rid of that h in the denominator. You will not be surprised to find out that we need to use the conjugate, So I'm going to do this so you can see the different color here, but the same thing that we've done before is coming back. We're going to multiply by 2 times x plus h minus 5 plus, and square root of course, plus the square root of 2x minus 5 over the same exact thing. So remember, I'm multiplying this by 1. That's what's really important to see here. Some students, don't see that. The reason that we're doing multiplying by the conjugate is because we can multiply by 1. And that's all I'm doing here. So I'm not changing what I have here in this limit. I'm just taking it and multiplying it by 1. I mean, 1, right? So it looks very different than 1, but it is 1 because I have the same thing in the numerator and the denominator. I can't do something to this function that fundamentally changes it, but I can multiply it by 1. So now I've got the limit as h goes to 0. So now we've got, as you can see, this times this, and that is our difference of squares. So you want to get really used to that idea when using the conjugate, that all it is doing is squaring the first two terms, which just take them out of the square root, and then it subtracts the last term, which we've now squared, and it's a square root, so it takes it out of the square root like this. So in one step, by multiplying by the conjugate, we've gotten rid of all of our square roots in the numerator. We did not, however, get rid of them in the denominator. That is okay. Do not get worried. So we still have them in the denominator. And if you want, it's not really, doesn't really matter, but you could multiply that out if you wanted to. I'll just multiply that out, 2x plus 2h plus the square root of 2x minus the 5, like that. Okay, now, we're on our way. So what I hope you see is, not surprisingly, this is going to help us in many ways, because we have 2x plus 2h minus 5 minus 2x plus 5. This is what happens. This is the point. So when we have the limit as h goes to 0, notice that what we have left is, because the 2x, subtract the 2x, and the minus 5 and the plus 5, all we have left is a 2h in our numerator, and then of course the crazy denominator. The denominator that's just very, there's a lot to this denominator. So 2x plus 2h minus 5, and then I guess I didn't want that parenthesis. Ow, we'll get rid of that too. There we go. Okay. And so let me just put back plus the square root of 2x minus 5, like that. Okay. And the whole point now, of course, is to see, I think I might have to write this one more time, that now the h simplifies. So that's, of course, the key thing here. We've got that h simplifying with that h. Now we no longer have a factor of h in the denominator. Now we're going to be able to take our limit and see what our derivative is. So the limit as h goes to 0, we've got 2 in the numerator. We've got still kind of a big denominator, but we're almost done. So we've got the square root of 2x plus 2h minus 5 plus the square root of 2x minus 5. Yay. All right, so now when we notice that there's no h in the numerator and the h in the denominator is not a factor. So now all we have to do is take our limit, and that just means plugging in 0 for h and seeing what happens. So this piece goes to 0, but that's the only thing that happens. So now what we have left is 2 over the square root of 2x minus 5. And notice we're adding to that another square root of 2x minus 5. So that's the same as having 2 of them. So we can write that 2 times 2, the square root of 2x minus 5. And then I don't have my limit anymore because I just took it, so I don't need it. And then, of course, you should see that you're simplifying those 2's so that we end up with 1 over the square root of 2x minus 5. And that is f prime of x.